can see what types of questions and the style that they're asked. The homework is also going to be due, and so there are two ways you can submit the homework. One, I'll put a link on Canvas. You can just upload it if you want to upload like a PDF file of the homework. Will be chapters, like we're looking at chapters 1 through 4 now. Let's see how far I make it through 4 today. And chapter 1 doesn't have any homework, so it's 2, 3, and 4, 3 chapters. And then the other way you can turn in is just by paper homework. If you have a notebook, you just leave it in the notebook. I just check it off. All I look for when I grade the homework is if you just attempted the problem. Most of the problems I assign are blue problems. The blue problems have worked out solutions in the book itself. So rather than leaving it blank, just copy the solution from the solution section, solutions guide section. And then you'll get full credit. All right, let's get started here with I forgot my pen. Problem solving in chemistry is by using dimensional analysis, where we have these relationships here. Like milliunits per unit, milligrams per gram, or milliliters per liter, something like that. We use those as conversion factors, and then we just string together a whole bunch of these conversion factors to convert from one unit to another unit. That's the main way. But there's other ways that we have to solve problems. One of the other ways is like this. Now, I was saying the other day, like if you have 0 milligrams, how many grams do you have? So if you have 0 milliunits, how many units do you have? 0 units. So those two zeros match up. So let's talk. If you have a 0 degree Celsius change, what was your Fahrenheit change? 32. Now, you have to be careful because I said change. If you have a 0 degree Celsius change, let's say, how much did the temperature change from yesterday? Oh, 0 degrees. There was no change, same temperature as yesterday. Would you say it was a 32 degree Fahrenheit change? So if you had a 0 degree Celsius change from yesterday, then that means it's 32 degrees warmer or 32 degrees colder the next day, Fahrenheit? No, that's a temperature change. When we do temperature change, then we use dimensional analysis. The dimensional analysis is 1.8 degrees Fahrenheit for every 1 degree C change. So there are almost 2 degrees Fahrenheit for every degree Celsius change. And so the conversion factor is 1.8 degrees Fahrenheit per degree Celsius. That, when there's a change, then that's the same 0. And therefore, we could use dimensional analysis to do that. And so if there are 100 degrees C temperature change, what was the change in Fahrenheit? 100 degrees C temperature change. Let's say it's 100 degrees C hotter. Then the Fahrenheit would have been how much hotter? 180 degrees hotter. Now that's different than the ambient temperature. The ambient temperature is offset by 32. So there's going to be a factor of 32 that you will have to add or subtract. And that means when we're looking at ambient temperature relating Fahrenheit and Celsius, you have to use the algebraic equation that we derived yesterday. And so let's take a look at that algebraic equation. And so most of the problems are going to be straight dimensional analysis, like the temperature change. So it doesn't matter where you start, where you end. It's 100 degree temperature Celsius, it's going to be 180 Fahrenheit change. He says for every degree Celsius, we have 1.8 degrees Fahrenheit. Which means, like, I have a European car. In a European car, I can adjust the temperature every 1 degree C. So, like, one day I'm driving and it's a little bit too hot. And so I click at 1 degree Celsius, and then it's a little bit too cold. Because I'm used to being able to adjust it Fahrenheit. Fahrenheit's finer tuning because if it's only 1 degree Celsius, that's like a 2 degree Fahrenheit. So I just dropped the temperature. So maybe it was like 76, not 74, or something like that. Whereas I have another car that goes in degrees Fahrenheit. It's much more fine tuned, so I could go 74 to 75. It's much more comfortable, rather than having to jump from 74 to 76, something like that. But anyway, those are temperature changes versus ambient temperature. Now, when we're talking about ambient temperature, if it's 0 degrees Celsius, then of course the ambient temperature would be 32. The temperature of the room would be 32 degrees Fahrenheit. And so we have to be or pay attention to temperature change versus ambient temperature. And so that's why I did this. So that's a little bit of a review there. Okay, the next thing we're going to look at is these proportionalities. Proportionalities are intensive, like proportionalities, 60 miles per hour. It doesn't matter how many hours, it doesn't matter how many miles, it's always 60 miles an hour. It's independent of the amount. Whereas the number of miles you drive and the number of hours you drive is not independent, it's dependent on it. And so, density is a proportionality. So let's say if you have 1 gallon of water versus 2 gallons of water, is it still 8 pounds per gallon? Whether it's 1 gallon or 2 gallons? Yeah, it's still 8 pounds per gallon. Now you just have 2 gallons, so it's going to be 16 pounds. So 16 pounds mass or weight is what we call extensive property. It's going to depend on how many gallons you have. But the density itself is not going to change. It's not going to be twice as dense, if you have 2 gallons. So those are proportionalities. This stuff, this is a lot of reading here. You can read that if you want. But let me move on to the next slide here. And so it sets up a ratio. And so the density is just this ratio here. It's a mass to volume ratio. M is mass, V is volume. And so we calculated the density of water. The density of water, the one we calculated was around 0.9 something, 0.99 grams per milliliter. Well, 0.99, that's so close to 1, people would round it to say the density of water is about 1 gram per milliliter. But it's not exactly 1 gram per milliliter because the density changes with temperature. The water does a weird thing. From 0 to 4 degrees, water actually contracts. And so water is more dense at 4 degrees than at 0. Because the water contracts, the density goes up. The density goes out, and then from 4 degrees to 100, it expands. And so the density, we can see this because the scientists like to see patterns, right? And so we can see this pattern here. If you take all that raw data, let's just go to density of water table. You take all this raw data, do you see a pattern there? It's kind of hard to see the pattern, right? You can kind of see the pattern. You see, we start off at 0.999843. And then we go up to about 4 degrees. Do you see the density went up? It went from 998 to quadruple 9. Do you see that? But then it starts to go down. This goes 75 to 67 to 43. So it looks like it's going down. And so what do scientists like to do next? They take all these observations and they start to look for patterns. And one of the most common ways that people look for patterns, is to do what? Graph it. And so they like to graph this here. And so we can see, oh yeah, the density peaks at 4 degrees Celsius and then drops here. So the highest density is about 1. You know, quadruple 9, we'll just round it to 1. And it depends on how many sig figs we want. And so if we go like 4 decimal places, quadruple 9 and then 8 or 7 or something like that. Quadruple 9, 7. So that's going to round. When we round this to 4 decimal places, it's going to go 1.0000. So that's the highest density. And then it drops. But does it drop all that much? No, it's not crazy. It's still, you know, if we were around this, it's still about 1. You know, to 3 sig figs is 0.996. To 2 sig figs, we would round this because we'd have to drop the 6. If we drop the 6, we would round up, right? And so the density of water is 1 gram per milliliter to about 1 or 2 sig figs. If you want more sig figs, then it's not. It's like 0.9 something, you know, depending on how many sig figs you want. How precise you want to know the density of water.
Are they saying why it's like that?
No, because that's the next step. So first we take our observations. This is a science. This is what scientists do, kind of. You know, if you don't come up with some brilliant idea just out of the blue, something strikes you, then it's a day-to-day grind. This day-to-day grind is you collect your observations, you look for patterns, and then if these patterns hold, the pattern, what we want to do is we want to define the pattern as because the most concise, you know, the way to most concisely define nature is by mathematics. So if we can break this into a mathematical equation, and actually we can, there's a mathematical equation. This looks like a parabola, doesn't it? Mm-hmm. Yeah, so you can just define it based on some kind of parabola. But where does that equation come from? You know, that's the next step, because the next step would be to start to think deeper. You know, we have this law. It's a simple law. It's just a mathematical equation. We have this simple law, which we call an empirical law, because the empirical law is derived. Once I get the equation, I can make any prediction. So once I have the equation for this, let's say I want to know the density at 56.3 degrees Celsius. I can easily do that. I just plug in 56.3 degrees Celsius into my mathematical equation that spits out the density. So laws are very useful because we can go ahead and predict what the density is rather than having to measure it. I'd rather not measure it. I'd rather not heat up the water to 56.3 degrees Celsius and then measure its weight and measure its volume. It's kind of a hassle, right? And so it's much nicer to be able to predict these things. But, you know, okay, the people are going to try to find violations of the law. This is like the laws of thermodynamics. Yeah, I don't believe that law, you know, and so they want to test it. But okay, but then there comes the deeper point. The deeper point is, you know, why does it observe this law? You know, and so that's where we come up with what's the next step in the scientific method? Hypotheses. We come up with a hypothesis. Unless you already hypothesized, could you have hypothesized that water does this? I don't know. Maybe you just had some flash and then you thought, oh yeah, you know. But I can't think of hypothesizing. And then so what is the hypothesis for this? And so that's where we go next. And then you want to understand the underlying theory, what's happening there. And so, but we don't have to. I mean, a lot of stuff. There's not enough people and not enough money and not enough time to understand everything. I mean, there's so many things that are just left to, okay, somebody in the future will figure it out, maybe, you know, something like that. I mean, if you think, let me just check if I got the right audio input here. Forgot to switch over to the microphone. Yeah, there's still so many things that aren't absolutely known. I mean, people often make claims that, okay, this is absolutely, you know, I mean, people make claims with zero uncertainty. It's very difficult to think of something with zero uncertainty. You know, this is how it's going to work. You know, there's zero chance of this happening. And, It was just kind of weird to think about because I just watched this on YouTube. There's a small chance that the universe could collapse into a vacuum. Have you heard that? And there was a recent physics experiment that showed that this happened, that this matter collapsed. They're thinking that the universe began not with like the Big Bang, but there's a vacuum and then these types of I'll show you the video about this, but it's pretty interesting. What is a vacuum? So they have the true vacuum, and then they have another vacuum. And the normal vacuum that chemists think of, there's no matter there, but there are fields there. But they're saying there's this quantum sponge in there, and this quantum sponge can create matter or engulf matter, and so there's no more matter left, and that's maybe the origin of the universe, something like that.
Very powerful.
So anyway, but that type of stuff, this theoretical physics stuff, we don't have to worry about because the theory that underlies chemistry is has been very successful because what should theories do? Theory should be able to do two things. What are those? Predict. Yeah, the theory should be able to predict things. And so, like saying, okay, this is water, but what about other liquids like ethanol? Should we measure it, or can we use theory to predict what the density of ethanol is going to do? So if you have some pure ethanol, does the density do the same thing, or does it do something different? That's what we want to use theory for, and then we predict it, and then you test it. And so, the theory of the chemistry has been very successful at predicting, and then people have tested it to see is the prediction correct or false, and it's survived. It's survived. It's not to mean there's always the fear that there's some result that's going to collapse the theory. That is, all of a sudden somebody will have an observation that the theory can't explain in that sense. But quantum mechanics, which is the theory that underlies chemistry, has been extremely successful. All right. So yeah, people will start to wonder, why does the density increase and then decrease in this manner? But we're not going to get there. All we need to know is the equation here, and that has to do. People will hypothesize this. Maybe they talk about it in some of these papers. I think they do here. So if you're interested in that, thermal expansion and density. Obviously, when temperature increases, you'd expect everything to expand, but why does when temperature increases, it contracts? That's counterintuitive. And so, really, this is easy. But how come it's nonlinear? Why isn't it a straight line? And then why are we saying this? This is counterintuitive. But there are reasons for that. You can read about the theory for that. Then why do people want to know? Because they want to predict. They want to be able to predict. This is like when I hear, okay, why? Like for example, if there's any kind of outbreak, whether it's an outbreak of a bubonic plague, the bubonic plague is common in California. In fact, or what's the other virus that killed some people in Yosemite recently? Did you hear about that? There's some virus from the rats, hantavirus. Have you ever heard of hantavirus? It's kind of a sad story because in Yosemite they have these little tent cabins, and it gets dusty. And so the housekeeping people, which are they just sweep the floor with the dust. Well, it turns out that there are rat droppings on the floor, and there's hantavirus, and they inhaled the hantavirus. And so a number of people actually died from the hantavirus in Yosemite. And so you think, okay, there's that virus outbreak in Yosemite, and there's also bubonic plague in the Sierra. And so you want to know how that spreads. People want to study this. And so, and that's normal, right? But weird things have happened recently. For example, like the coronavirus, not nobody, but some people don't want to know how it originated or how it spread. It's weird. It's just counterintuitive to science, it seems. It's just, you want to know. so you can make predictions, so you can prevent stuff from happening in the future. We want a good theory of what's going on, or at least a good hypothesis, or at least competing hypotheses to understand such things. And so science has gotten a bad rap lately because science has lost a lot of public trust, they say. Have you seen the articles about this? Maybe? There are a lot more people skeptical of science, but science itself, the method, has been proven to be extremely successful. Science has, from Lavoisier's time, has changed. Uh, I think change things for the better, of course, especially with technology. All right, so anyway, we'll get back to this. For chemists, density is in grams per milliliter or grams per cubic centimeter, the same thing, right? Milliliters and cubic centimeters are the same. Exactly. Although some people like to use milliliters for liquids and gases, and cubic centimeters for solids, but it doesn't really matter. You could use milliliters for solids as well. But we do this, we can measure densities. I told you, what are the three most, or what are two of the most dense elements on the periodic table?
OS and
Yeah. Osmium and iridium. Do you know approximately their density? You should know the approximate density of water. What is the approximate density of water? One gram per milliliter. Now, the density of osmium and iridium, those are like 21, 22 grams. So they're 22 times heavier. The density of gold is about 20 times. So gold weighs 20 times more than water per milliliter. And so a gallon of water is 8 pounds. A gallon of gold would be about 20 times that, 160 pounds. Right? That would be pretty hard to carry. If you had a 1 gallon jug of gold, that's 160 pounds. Could you lift that with one arm? Yeah. 2 arms, it would be still pretty difficult to lift, wouldn't that? A gallon of gold? I guess, yeah, if you're training, I've been training, then sure. So we need to know approximate densities. So most solids aren't as dense as gold. Most solids are around as dense as like salt. What's the density of copper, roughly? You forgot 8. You don't have to know it so precisely. 8.96, but it's around 9. It's around 9 grams, 9 times heavier than water. Aluminum's density, it's a lot less dense. It's a lighter metal, right? Aluminum's density is around 2.7, about 3 times heavier than water. But most solids are about twice as heavy as water. So you throw a solid in there, except wood. Is wood heavier than water or lighter than water? Wood's lighter than water, it doesn't sink. So wood's density has to be less than 1. And so wood's density varies from about 0.5 to 0.7, depending on what kind of wood we're talking about. And so what we want to know is we don't want to have to memorize a bunch of densities, but we should know how densities vary. And so if we take water, this is okay at 2 sig figs over that temperature range, this is okay. But if we want to be more precise, then we're going to have some 0.9s in there, probably. And so to 2 sig figs, most people know the density of water. Wood, like pine, is about half as dense. Maple, 6/10. Oak is much more dense. Oak is a hardwood, 0.8. Glass is about 2.5. Aluminum, 2.7. So a lot of solids are 2-3 times heavier than water. Iron is about 8 times heavier. Copper is about 9 times heavier. Silver is about 11 times heavier.
What does ATM stand for, sorry?
ATM stands for atmospheres. Did I told you the normal pressure, atmospheric pressure? 14.7 pounds per square inch is normal atmospheric pressure, which is equivalent to a column of mercury. A column of mercury, 760 millimeters tall, weighs how much? If you put that in your palm of your hand, it would weigh 14.7 pounds per square inch. We call that 1 atmosphere because that's normal atmospheric pressure. And so those would be equivalent to 1 atm. And so when we measure density, we need to know the pressure because if we're under thousands and thousands of atmospheres of pressure, it's going to squeeze things down and compress the volume. And so there are people who work at tens of thousands of atmospheres. They use a diamond anvil. Have you heard of a diamond anvil? They use diamonds because diamonds are one of the hardest materials, one of the hardest substances around. Do you know there's stuff that's harder than diamond, though? You know, diamond gets a 10 on the Mohs hardness scale. Have you heard of the Mohs hardness scale? So, but there are things that are greater than 10. But diamond is, yeah, is one of them. The things that are harder than 10 are they have some other constraints. You know, diamond is what we call isotropic. Isotropic means non-directional, but there are things that are directional that are harder.
What does that mean?
Non-directional means like graphite is weird. Graphite is occurs in layers. And so if you're within a layer, you can slide the layers one on top of each other. But if you're perpendicular to the layers, then it doesn't slide this way. So graphite's kind of weird. Graphite conducts electricity. It conducts electricity only in the horizontal plane. But if you try to conduct electricity perpendicular to that plane, it's an insulator. Graphite transfers heat. It transfers heat in the horizontal plane too. But it's a poor heat conductor perpendicular to it. And so those are what we call anisotropic. Anisotropic just means it's directional. Diamond is isotropic. It's hard in all directions, so it's a 10 every way you do it. But there are harder materials that are only greater than 10 on one surface, but on another surface, it's less than a 10.
Diamond in general is hard, but some are hard.
Yeah, in particular areas. So there's things that are harder than a 10 on the Mohs hardness scale. One of them, when I was at UCLA as a student, the professor I was working with, I visited him a couple of years ago, and he was telling me about this material that they made in their laboratory. This material is harder than diamond. And so how do you sharpen diamond drills? These diamond drills are used for drilling like oil and that kind of stuff, but they get worn out. And so they're thinking, how do you sharpen those? And he made this material that they use to sharpen things that are harder than, you know. And so it's quite. He has actually done a lot of interesting things since I left UCLA, and he gave me a little update about what he's doing now. But he's done some pretty impressive stuff, including the graphite. You know, they stick things between the layers of the graphite. It's like a sandwich. So they make a graphite sandwich, and they use those in batteries. And so they put lithium in the sandwich, and they have a lithium graphite sandwich. You can't eat it, though. You know, worry about those catching on fire as well. It's to store energy. You store energy by making a sandwich. It looks like a peanut butter and jelly sandwich. Except the one he made a new material that is very rapid. So rather than waiting, you know how, like I have an electric car. So over here at El Camino on the first floor of the parking lot, there's a plug-in, right? You can charge your car. And then I charge my car an hour and a half, and then actually after an hour and a half, do you know how many miles of range I got? After an hour and a half charging, I got 20 miles, 20 to 26 miles of range. That was at an hour and a half. I just needed enough to get home because I forgot to charge it at home. And a lot of people can't charge it at home because they don't have enough power. You know, our breaker panel So basically, you have to sacrifice something because there's a certain number of amps in your breaker panel. And if you want more amps, then you have to go from the street to your breaker panel and build another circuit there to carry more amps. So what we did for our breaker panel is we got rid of the electric dryer. There's a circuit for the electric dryer, got rid of that, and then used that for electric car charging. But I wonder how other places are going to do this. Over here, we don't have to worry about it because the charging rate over here is 6 kilowatts per hour. You know, at the Tesla supercharging, they get closer to 100 kilowatts, and at some of these other ones, Electrify America, you can get more than 100. They climb up to 150. Some of these can climb up to 300. And so, so over here, if I went over to Target, Electrify America over here, then I could get like 20 miles in like 5 minutes, you know, because it's charging at 150 kilowatts per hour versus over here in the parking lot. But that's okay. I mean, I just needed 20 miles, so I just waited an hour and a half to get the 20 miles to get home. But anyway, we want to know something about the densities. So get a range. So some of the most dense elements. Here we have gold. You know, it's hard to remember these precisely, so you just remember ballpark. You know, ballpark, the most dense element is
Iridium and
iridium osmium. What is the density? Actually, let me just do that. It's a toss-up. Is it iridium that's the most dense, or is it osmium? Iridium, most 22.59 for osmium. Osmium is the densest naturally occurring element. It's not tremendously more dense than gold, you know, about 22, 23 grams per cubic centimeter. But if you had a gallon of osmium, it would be hard to carry. What are the 3 most dense elements? These are gases. I don't want gases. Here they say, while the densest element is either osmium or iridium. Well, what do they mean either? It's one or the other, isn't it? But the situation is sometimes things occur in different arrangements. Those arrangements we call different structures. So for example, pure carbon occurs as diamond, or pure carbon can be graphite. And so sometimes there are what we call allotropes. Allotropes are the same element but different structures. And so it depends on which allotrope. You know, water, ice, how many different forms and densities of ice there are? You know, if you go down, let's say to the bottom of a glacier, do you know the ice crystal is different than the ice crystal at the top? That's because of the pressure. You know, it compresses the ice, changes the structure a little bit. And so there are different forms of ice. Let's see, number of ice phases. We call it phases. 19, can you believe that? There are 19 different crystals of ice, depending on the pressure and the temperature. And so you can see different ones over here. Do you see the arrangement of the water molecules? And so obviously that's going to change the density. So the density of ice it depends on where you get the ice. You know, that's going to change the density of ice. But under normal conditions, we just say, oh, ice, an ice cube from the freezer. Well, ice cube from the freezer, how many air pockets are in there? A lot. A lot. And so what we need is what we call single crystal. You know, nothing that can get contaminated with air. You know, that's the best, and then measure the density there. So measuring density can be tricky because it depends if you have lots of little crystals or one big crystal, you know, and then air getting trapped in there, or empty void spaces, we call it. Now, gases are a lot less dense. And so gases are 1,000 times less than. And so air, for gases, we like to go grams, not grams per milliliter, because this would be grams per milliliter. We want to go grams per liter. And so there are 1,000 milliliters per liter. So if we multiply this by 1,000, in other words, we move the decimal place 3 places. Air has a density of 1.2 grams per liter. So if I have a liter of air, it would weigh 1.2 grams. Well, obviously that's the density of air under what kind of conditions? Well, what we say is this is under normal ambient conditions. And so the density of air changes with temperature a lot. And it changes with pressure. And so the air is a lot thinner at high altitude. Because high altitude, at the top of Everest, the pressure should be about a third of an atmosphere. A third of an atmosphere is very thin air. And so the density is going to be about 1/3 this. And so 1/3 this would be like 0.4 grams per liter versus 1.2 grams per liter. And that's a lot less oxygen. A lot of people breathe the oxygen there. But even the people who breathe the oxygen, they say that this is the death zone. If you don't have oxygen, then you're on a path to death, and you got to get out of the death zone as quickly as possible. Otherwise, you will die. Is what they say. Even if you're going to be highly acclimated. And the people who don't really Everest is like a tour destination now. And there's these long lines of climbers going up. A lot of them are just guided. They aren't quite in shape. And so there's been a number of tragedies there. Air on Everest if it's 0.4 grams per milliliter, that's a lot less oxygen than at sea level. At sea level, it's 1.2 grams. Helium is a lot less dense than air, 0.17 grams per liter. Mm-hmm.
Is there anything like that
Yeah, if it's a gas, then it's typically about a gram per liter. Some gases are going to be heavier, like helium's really light, but argon is heavier than air, so it sinks. I think helium's heavier than air too. Helium's lighter than air, so it floats out in the air. Argon's heavier than air. I used to use lots of argon. And argon is nice to use because it's heavier than air. But they're all around 1 gram per liter. The solids, these solids are going to vary from some lighter solids like lithium, beryllium, to some of the heavier solids like iodine, beryllium. So it's going to vary. I think lithium will definitely sink in water, so more maybe like 2 grams per milliliter. Definitely 2 grams per milliliter. And there's nothing in periodic table. You can buy fancy periodic tables that have the density there. One of the fanciest periodic tables that I really like is the. Did I already mention this? This is Sargent-Welch periodic table of the elements. This is 2 sides on this. This is one of my favorite periodic tables here. Sargent-Welch. It gives a lot of data. That's the reason I like it. Okay. A lot of data on the elements. So from this you could figure things out. It'll give I think it gives the density. And then this is page 2 of the Sargent-Welch. It's double-sided. Page 1. The page 1 looks like a normal periodic table, but it gives more. Like, for example, take a look at carbon. Do you see what it gives there? The range. This is kind of nice, isn't it? +4 to -4. These are the common ones, 4 and 2. Yeah. Nitrogen, the range is -3 to +5. And these are the common ones that you see. Okay. minus 3 then fixed charge. So then it gives some other stuff in there that's pretty nice. I like it. And then they still use the Roman numerals. I don't know why they got rid of the Roman numerals. Most modern periodic tables got rid of these, but these are coming very handy. Maybe it's too much information overload, and so that's why they got rid of them. But those Roman numerals, especially here in what we call the transition metals, are very handy to have in Chem 1B. You can do things very rapidly when you know these numbers. But this is the Sergeant Welch periodic table, the element. They sell these at the bookstore, like UCLA bookstore or something like that. It's not that expensive. That's where I bought it when I was a student. I just bought it in the bookstore. And then just kept it in my binder. You have a if you bought the paper edition of our textbook, it has periodic tables that you can use. Which are pretty handy. This one's not allowed on tests, unfortunately. We have different kinds of alcohols. This is methanol. Methanol, is that the alcohol that's in alcoholic beverages? No.
Medicine? Medicine or like papaya?
Yeah, methanol is in medicine. Methanol is in sterno stoves. Have those sterno stoves? They have a little flame for caterers, that kind of stuff. But some people have, if you drink methanol, you know what can happen? Yeah, you can go blind. But that's not urban myth. That's true. If you drink methanol, you can go blind. Or you could die. Why would anybody drink methanol? Yeah. Why would anybody drink methanol? Do you know what wood is made out of? Methanol? No. Wood is not made out of methanol. Do you know wood is made out of glucose? Do you know what glucose is? Sugar. So if you ferment sugar, you can make alcohol. So if you just take sugar, like this is what, in organic chemistry, when I was a student, this is what we did. We got some sugar, yeast, and started fermenting it. And then we made alcohol, ethanol, and then distilled it. And so at the end, we had as pure of alcohol as we could get. Because distillation wasn't perfect for alcohol, ethanol, we could get 95% ethanol. 95% ethanol is 180 proof. So we made some 180 proof ethanol, which I think they call that moonshine. And so we collected these in little sample vials, and then you had to do the taste. What does moonshine taste like? Because normally you don't taste anything in the chemistry lab, and I don't recommend tasting anything in the chemistry. Don't put anything in your mouth. But this one, I did taste it. But the thing is, it's so volatile that when it hits your tongue, it just evaporates. And so it wasn't like, it wasn't anything particularly. I mean, it was kind of cool that it evaporates so fast, but no, ethanol tastes sweet. Do you know that? Yeah, a lot of people like the taste of ethanol and the smell of ethanol, right? Uh-huh.
I love a lot of different kinds. So it's like stuff that they put in there. Like poison someone and Gatorade.
Yeah. Oh, that would be another alcohol.
Right?
That would be methanol. Methanol, yes, they can do that to poison people and kill them.
I just watch a lot of shows.
And then another alcohol called ethylene glycol. Have you heard of ethylene glycol or propylene glycol? That's another alcohol that's also poisonous, but they use that one in antifreeze. So that's an easier one to do. for But the thing is, if wood is made out of sugar, then why not ferment wood? And so that's what people do. And so do you know what they call methanol? They call it wood alcohol, because if you try to ferment wood, this is the alcohol you generate. Versus if you try to ferment sugar, you make ethanol. And so some people try to ferment wood and then either drink it themselves or sell it. And so this is one of. Did you hear about those U.S. tourists that went down to Mexico and they had some drinks or something? They're suspecting maybe that's methanol, because do you know the number of methanol deaths in the world? So let's look at the list of methanol poisoning. You know, Australia, 2013, 3 people died and 1 suffered partial blindness when they ingested a homemade beverage containing methanol. That's 2013. This is not so long ago. Actually, there was a more recent case, I think in 2017. Well, this is Australia. Let's see the other ones. Brazil, Cambodia, Costa Rica. I think the Ches, there was something more recent. 38 people died. Hey, don't drink any, or just be careful what you drink when traveling.
And they were vibing in El Salvador or what?
El Salvador, Estonia, 68 people.
The other one had 122.
122.
El Salvador.
El Salvador, 122. Adulterated with methanol. How about the U.S.? Yeah, 156 died.
It's in India. That whole thing's Indian. That whole list is all India.
Oh, Indonesia. Okay, I got to keep going. Keep going down. I think this was 35 in 2020. In one mass methanol poisoning event. They were using methanol in hand sanitizers, and people were trying to extract the methanol from hand sanitizers to drink it. But in the U.S., methanol is banned in hand sanitizer. You're only allowed to use ethanol in hand sanitizer to prevent people from trying to drink alcohol from the hand sanitizer. And then the U.S., it happened as well.
All the way at the bottom.
Yeah.
There.
31 deaths in Philadelphia. That's 63. This is 2018, Massachusetts. You see, this is false advertising. Ethanol extract. This would be 180 proof. You would expect this to be moonshine. Unfortunately, it wasn't. They probably fermented wood in addition to sugar and got a mixture of methanol and ethanol. And you got to be careful about some of these things. So FDA recall. This is a person who bought this online. It looks like bought over the internet and delivered. So I wouldn't trust it either. You know, somebody was selling me like 180. Maybe, huh? Maybe if you go to Nevada and buy it straight, because I think you can buy it in Nevada if you want to buy 95% ethanol. We have 95% ethanol in our stockroom, but what they do is in order for them to sell it without the alcohol tax, they have to adulterate it. And so what they do with our ethanol is they put like a carcinogen in there so people don't drink it. And so it's slightly contaminated with things to prevent from consumption. Otherwise, they have to put a thing there and charge tax on it. We also have 100% ethanol. 100% ethanol is hard to get. So we use 95% ethanol in the lab all the time. But I tell people not to drink it. I don't know if that's true or some kind of urban myth that it's adulterated, but I think it is true because Because it says it's extracted. This is ethanol is extracted with methylene chloride, which is methylene chloride is a potential mutagen and carcinogen. So probably don't want to drink it. But I think you can smell it if you want to smell. It smells like yeah, Russian toaster warning people. But how do you know it's adulterated or not? That's a mixture. And what can you do with mixtures? Are they easy to analyze, mixtures? No. You could try separation techniques. So there are different separation techniques that you can do. Actually, they're easy to analyze if you have the equipment. And so let me go here. One powerful technique for separating mixtures into the components is chromatography. So, for example, if you have different inks, let's say you have black ink. Is that pure? Maybe it's pure. It looks homogeneous, but it turns out it's not pure. It's made up of other inks. And you can separate these using chromatography. This is like alcohol or water or something. It carries them. And so we have different types of chromatography. This is called column chromatography, where you try to separate out the mixtures. So here you have something that looks homogeneous, but when you pass it through the column, you see it separates into different components. And the components, they separate because they have different properties. And so chromatography could be a quick way to determine if your what you think is ethanol is what you're getting, because mixtures are very difficult to analyze. We want to separate them into the components. We want to know what the composition of the mixture is, how many of each component we have. And the way we do that is by using percent by mass or percent by volume composition. So that's what we're going to talk about pretty soon. Here, the mass of 50 milliliter sample of methanol is 39.59 grams. So if we take the mass divided by the volume, we get the density. So here's the mass divided by the volume, we get the density. But this is how many sig figs here? How many sig figs is this? 50 milliliters. 4. They should write it as 4 sig figs here. So this is something I don't like because they wrote it as 1 sig fig here. They should have written it as 4. That means we are allowed how many sig figs here? 4. But if this were 1 sig fig, then we're only allowed 1 sig fig here, and we'd have to round this to 0.8.
The bottom is not infinite?
What's that?
The bottom is not infinite.
The bottom is not infinite. The bottom is not infinite because that comes from measurement up here.
If there was no measurement,
Then it would be infinite. So now it's infinite. Here, this is now infinite. This is grams per 1 milliliter. So how many sig figs are there in 1 milliliter? Infinite. And so what we read this is in exactly 1 milliliter, there's approximately 0.7918 grams to 4 sig figs. So that's where we do the infinite thing. But here, since both of these numbers came from measurements, we know. The density of a certain machine oil is 0.910 grams per milliliter. So again, 1 milliliter is infinite, and we have 3 sig figs here. This 0 is not significant, this 0 is significant because it's after a decimal and after a non-zero. So that's 3 sig figs. Find the volume occupied by 196 grams. And so we start off with 196 grams because that's extensive. And the 0.910 is intensive. So we'll just do 196 grams of oil, 1 milliliter. This is exact. This is not exact. 0.910 grams. The grams cancel, that leaves us with milliliters. 215. So we got 3 sig figs, 3 sig figs, infinite sig figs. We're going to have 3 sig figs in our answer. So this is just a basic, what we call one-step conversions. All right, let me go to the next. I don't know if I downloaded next PowerPoint. didn't. So we'll do some more practice with dimensional analysis. There's one other technique to solve problems in chemistry, but let me dig into this first. I guess I should download it already. I'll talk about, so the two common techniques that I discussed for problem solving are one, dimensional analysis, and two, algebraic equations. The third common technique is when we have a system of equations, that is two equations and two unknowns. Well, we'll move on to chapter 4 for right now, Introduction to Gases. We already have been talking about gases in terms of the particulate level, at the molecular level, and then the macroscopic level, and the properties there. But we'll move on here to the characteristics. We talked about gases can be expanded or compressed. Gases have low density, 1,000 times less than, let's say, water. Gases may be mixed in a fixed volume. So gases we can mix in all proportions, so there's no limit to gases. Like, some things will have a limit. Can you mix any number of sugar cubes into a cup of coffee? You know, have you ever tried? What is the maximum amount of sugar you can dissolve in a cup of coffee? 2, 3, 4, 5? Yeah. You can just keep trying, but it's not infinite, correct? So if you have a gas, can we mix any amount of oxygen? Let's say I want lots of oxygen in my air. So can I put more oxygen in the air? Actually, I can. It's mostly empty space, so I can add as much oxygen in the air as I want. In fact, I can add so much oxygen that it's almost like pure oxygen. And so those are what we call miscible. Certain things are miscible. Like, for example, if you mix water and water, is there any limit to how much water you can mix with water? No, they're miscible. Well, there are certain chemicals that behave like that. You know, they're so alike that you can just mix them in any proportion you want. And so this is what they're talking about here. Gases may be mixed in a fixed volume in any proportion. There's lots of empty space there, and so you can fix it. But it will change the pressure, though. Gases exert constant pressure on the walls of the container uniformly in all directions. These you don't have to worry too much about. But here's the macroscopic. We can compress a gas by adding weight. We can expand the gas by removing weights here. And we can expand it further by pulling on this and creating a vacuum. And so these are just the molecules of empty space, less empty space, more empty space, and a lot more empty space. Creating a vacuum does require work, though, because this, you have 14.7 pounds trying to force this down. This is more than 14.7 pounds. This is 14.7 pounds plus whatever this weighs. Here's the difference: solid, like the iron nail, liquids like the water, and gases like the balloon. The differences, we'll try to visualize the differences. This is not in motion, but you can imagine what the motion is. Gases have low density, about 1,000 times less than liquids. We can mix gases easily, so if I wanted to add some green gas here, it's no problem. But when I have the green gas here, what happens is it increases pressure. So right now, what pressure is caused by the collisions here. And so we fill these collisions. The force equations per unit area is what we define as pressure. So now we're going to have twice as many collisions because we have twice as many molecules. And so we're going to just double the pressure. So if we double the number of molecules, and we double the equations, and we double the equations, we double the pressure. So we can mix it, but we're going to have it at higher pressure. Gases, since they're moving in all random directions, they're going to apply equal pressures on the top and the bottom and on the side. Whereas liquids will go to the bottom of the container. And so liquids will be heaviest at the bottom and then lighter near the top. You can feel the pressure. Like say if you're in a swimming pool and you go like 3 feet deep versus 9 feet deep. If you go 9 feet deep, can you feel the pressure of all that water? It's going to weigh a lot more. So this is the basic kinetic molecular theory of gases. Gases consist of particles. I call particles because they don't have to be molecules. For example, helium doesn't form molecules. Helium just forms atoms as a particle. Whereas nitrogen and hydrogen form molecules. So not everything forms molecules, so I just call it, but it's called kinetic molecular theory here. But maybe kinetic particle theory might be better, since not everything makes molecules. But it doesn't matter, as long as you know that molecules doesn't mean strictly molecules. So gases consist of molecules in empty space. The volume occupied by molecules in the gas is negligible when compared to the volume of the space they occupy. So most of the space in this room is empty. The gas particles themselves, if I were to take all the gas particles in this room and liquefy them, what would the volume be? The volume would be very small. Because there's so much empty space in this room, so I'd do that. Although we fill it. And so we could liquefy air by cooling it down and make liquid air. There's a company called Liquid Air. Attractive forces among molecules of a gas are negligible. We'll have to talk about this later. So average kinetic energy of gas molecules proportional to temperature. In other words, kinetic energy is proportional to temperature in Kelvin. So if something has 0 degrees Celsius, does it have 0 kinetic energy? No. Because zero is not absolute. If something has a temperature of 0 Kelvin, does that have 0 kinetic energy? Yes. Molecules interact with one another in the container and the walls without loss of total kinetic energy. We're going to talk more about this later, so don't worry about it for this test. And this is a liquid, and we're watching the liquid. And when we watch the liquid, there are always about 100 molecules of water in the little microscope window here. This would be a very powerful electron microscope type thing. Over here, we watch this little space for gas, and nothing happens. There's nothing, and then boom, a water molecule passes by. This is steam or gas. And so these are just different snapshots taken. Okay. This is just to illustrate that the gases are mostly empty space. It's not a vacuum. It's not a vacuum because you're going to feel the pressure. Eventually, this particle is going to strike the wall of the container and cause pressure. If there's nothing in there, then if this were a vacuum, in fact, I have my demo I'll set up after. But if this were a vacuum, then we have no weight on the inside, but we have almost 15 pounds on the outside. So if you were to put 15 pounds on top of this glass, will it break? Yeah. Probably not. But it depends. If I take a piece of paper and put 15 pounds like this and hold it, do you think the paper will tear? Yeah. So it depends on the strength of the container. So a thick Pyrex glass like this probably won't implode. Probably won't implode, but maybe will. You have to watch out. People who work with vacuums, what they do is they attach pumps to this and then suck out the air. And you always got to worry about vacuum implosion. This is like being on a submarine deep underwater. There's a big differential. And you don't want the submarine to implode like, what was the submarine, the carbon fiber one? Ocean Gate, yeah. That was pretty scary. Well, the same thing that happens in labs. You can get implosions. And when I was at UCSB, there was an implosion. But fortunately, nobody was inside the lab, but it was all made of glass. And it was really weird because they said about 3 feet above, all around the lab, 360 degrees, was glass shards all the way around. And so if somebody were standing there when the apparatus imploded, they would, at 3 feet up, they would have gotten shards of shrapnel in that implosion. So even though, yeah, it's probably not going to implode, but, I'd still be careful. So when we talk about pressure is like pounds would be like force per square inch. The effect of the force comes from collision. And so if you increase the temperature, the molecules are moving faster. If the molecules are moving faster, the force of the collision is going to be greater. And so at higher temperatures, we expect that. Or if we have more gas, it depends on the pressure of the gas. The higher the pressure means we have more gas molecules. The lower the pressure means we have. And we can keep lowering the pressure, lower the pressure until we get to zero. So the factors that affect the pressure of the gas is the volume. If you expand the volume or contract the volume, if you make the volume smaller, you still have the same number of particles, but now a smaller space means they're going to collide more frequently. The amount of gas and the temperature, so these things will impact. But you don't have to worry about this. We'll talk more about this later. And then we talked about the barometer. The barometer works like a balance. On one side of the balance, you're weighing the air. And how much does the air weigh normally? On the other side, you're weighing the liquid mercury. And so right now it's balanced because liquid mercury isn't going up or down. And so if we have 14.7 pounds, then the weight of 760 millimeters of mercury will be 14.7 pounds. So if you were to hold this in your palm of your hand, you would feel 14.7 pounds. There's a vacuum here, so there's nothing above that. But we do liquid pressures. Usually, you know how they achieve the vacuum? That's a good question because it's very hard to make a vacuum, right? And so the way they achieve the vacuum at the top is this. You wouldn't want to do it in exactly this manner, but it's essentially this manner that they do it. You fill a test tube-like thing with mercury all the way to the top. And so we fill this with mercury, and then you plug it somehow. Let's say you plug it with your finger. So you plug it with your finger, and then you flip it upside down, and then put it into a pool of mercury, and then remove your finger. Then this used to be filled only with mercury, right? Only with mercury. And so if you look at the barometer, it's like 800 millimeters. And so, or more than 800, let's say 900 millimeters. And so now we invert this, flip it upside down, put it in a pool of mercury. There's no air in there. It's all mercury. But if we have 900 millimeters of mercury, it weighs too much. It weighs too much. Because outside we have 14.7 pounds, inside we have too much. And so what's going to happen? Yeah, some of this is going to drain out. When it drains out, what's left behind? A vacuum. There's no air in there. There's no air bubbles. If you have an air bubble in here, then forget it. There's going to be air in there. It's not going to be a vacuum.
Mercury is kind of dense, right?
Yeah, mercury is dense. Now, is this a perfect vacuum? No. Unfortunately, it's not a perfect vacuum because do you know mercury vaporizes too? It's not very volatile, but it will vaporize. It's like the ethanol. When I tried to drink the liquid ethanol, by the time it hits your tongue, it's like vaporized into gas. So you can inhale the mercury. I mean, not the mercury. You don't want to inhale mercury, but you could inhale mercury. You could inhale mercury because if you're trapped in this, it's not a pure vacuum. There's mercury vapor in here. You know, it's like these fluorescent, the old fluorescent lamps had mercury vapor. There's a little bit of liquid mercury in there that they get hot enough to vaporize, and then they get mercury vapor. So this is why, you know, you're not supposed to throw away fluorescent lamps in the garbage because we don't want to contaminate things with mercury. In fact, disposing fluorescent lamps is a headache because who takes them now? You have to pay somebody to take them because they have to dispose of them as hazardous waste. You know, I remember I was like driving and I saw somebody at the dumpster breaking a whole bunch of these mercury-filled fluorescent tubes and dumping them into the garbage dumpster just by throwing them in there and they break open. And I thought, good thing most people don't do that. Because mercury is a heavy metal and causes some brain problems. Lots of people used to work with mercury. We used to have mercury thermometers. We used to have mercury thermometers, but they were broken too frequently. And then you have mercury. Mercury's hard to clean up because it just balls up and spreads everywhere, forms these little balls, and they roll all over, and they get caught in the cracks. Wow. I'm not sure what our mercury levels are in the air in the lab, but the labs were remodeled. Then we switched to alcohol. So if you broke a thermometer, one of our thermometers now, it's just alcohol. Alcohol expands and contracts with temperature, more so than water. You know? And so it's easier to measure. Then you just calibrate it. All right, let's stop here. We'll take a break. Yeah. Are you finished with the quiz? Yeah.
Is there going to be a quiz towards the end of the day?
Yeah. We're gonna have another quiz today. That was the question. So properties. When we characterize a gas, we want to know the pressure of the gas, the volume of the gas, the amount of gas, and temperature.
So is the quiz today going to be the one that we were taking on Monday, or is that entirely new quiz?
Well, it looks like a lot of people have finished. In fact, it looks like most people have finished the quiz from Monday. If you haven't finished, then you can work on that, and then I'll have a new part to it. But I think I have most of the quizzes here. But if not, it's all right. You finish it, and then see. So if you were to buy a tank of air, like say an air tank, you know, and you go to buy an air tank or a helium. Let's say you go to buy a helium tank, and they sell you, let's say, one of those 2-gallon tanks or whatever those are, 2.5-gallon tanks you can buy. And you're going to buy 2 gallons of helium. You have to worry because does the possibility exist that that helium tank is essentially empty? Is that possible? Yeah. I mean, they could sell you helium, but so we don't usually buy helium by the volume. If you buy by the volume, you don't know exactly how much helium you're going to get unless you know the volume and the pressure. Because if you were to buy a tank of helium and the pressure reading were 0, is that a good deal? Even though it's 2 liters? No. And so what's probably better is to know the amount. You know, how many grams of helium or how many helium molecules. Actually, helium doesn't form molecules. How many helium atoms are in that sample? And each helium atom would have a mass, and then we could just figure out the mass of helium that we're purchasing. If you were to buy a tank of helium, you want to know what the pressure is. And so here we have atmospheric pressure. This is normal atmosphere. 1 atmosphere is the unit of pressure based on atmospheric pressure at sea level and capable of supporting a mercury column 760 millimeters high. So 1 atmosphere is equal to 760 millimeters. This is exact. A torr is used to replace millimeters of mercury. And so rather than saying millimeters of mercury, we could say torr. So 760 torr is equivalent to 760 millimeters. It's just another way of expressing millimeters of mercury. This is named after Torricelli, who did the barometer thing. But that's not the SI unit. The SI unit of pressure is Pascal. And the Pascal has a physics definition. It's 1 Newton of force per square meter of surface area. And so that would be a Pascal. Now, Pascals are kind of small. So 1 atmosphere is equal to 101,325 Pascals exactly. So this is exact. Wow. Let me make these all exact. Oh. These are all exact. Pascals are a bit inconvenient, so what they do is they convert this into bar. And the bar is just moving the decimal 5 over. So this is 10,000. And so this is equal to 1.01325 bar exactly. And so what we get is 1 atmosphere and 1 bar are about the same. So if we say that normal atmospheric pressure is 1 atmosphere, that's about 1 bar. It's about 1 part out of 100, so that's about off by 1%. So roughly the same. And so what people typically do is they measure pressure in atmospheres and they measure pressure in bar. Now bar is the SI unit, so there's a push to switch to the bar. And so in the USA, we like to use atmospheres. But in the rest of the world, they like to use bar. I happen to think that the atmosphere is better. Why? Because if somebody says, what is normal pressure? You know, normal room pressure? What do you want to say? Do you want to say 1 atmosphere, or do you want to say, oh, it's 101,325 bar? Atmospheres. I much prefer atmospheres. But you can prefer bar. You just have to memorize it's 1.01325 bar is normal atmospheric pressure. And so bar is a little bit smaller than an atmosphere.
Is that about bar or infinite?
It's infinite.
No, sorry. 1 atmosphere is 1.1.
Oh, I'm saying, okay, what I mean by this is that 1 atmosphere is about equal to 1 bar. That's what I'm trying to say. They're about the same. But if you want to do SI, then we'll talk bar. They talk bar and millibar. Have you heard of millibar? A millibar is, yeah, and so we multiply this by 1,000. So this is normal atmospheric pressure is 1,013.25 millibar. Okay, do you want to memorize that? Well, what's easier to memorize, 760 millimeters of mercury or 1,013.25 millibar? So normally what I do is this. The most important stuff that I think is this, 760 millimeters of mercury. So atmospheres to millimeters of mercury to torr. That's easy to remember. And then this one I like to remember. That is the conversion from atmospheres to bar. 1 atmosphere is equivalent to 1.01325 bar. This one you don't have to memorize. This will be in general given. There's a lot of digits to memorize. One bar, though, itself, now we're not comparing this to atmospheres, but 1 bar is equivalent to 100 kilopascals, or 100,000 pascals. The pascal is the SI unit of pressure. Here, pascal. This one you don't have to bother memorizing. Inches of mercury, we don't have to memorize this one. This one we could derive. The way we derive it is like this. 760 millimeters is 1 atmosphere. And then we go from millimeters to centimeters. Yeah, there are, in 1 centimeter, there are 10 millimeters. And then we go from centimeters to inches. And it's exactly, 1 inch is exactly 2.54 centimeters. And this is going to give us 29.92 inches of mercury. So I don't bother. This is just converting from millimeters to centimeters, centimeters to inches, and then we have inches. So, so 760 millimeters of length is about 30 inches long. I told you 14.7, but it's actually a little bit more precise. It's 14.70. This is not exact, I think. As I recall, this is not. It's like 14.69 something something. And so this is 4 sig figs. It's not infinite sig figs here. This one you don't have to memorize. Yeah. So if we want to measure the pressure in this room, we use a barometer. Did anybody take a look at the barometer? Try to measure it? Nobody? I guess not curious enough to want to see. Well, the barometer's there fixed on the wall, but you know you might need that pressure. You need the pressure? Maybe not. So an open-end manometer is similar to a barometer. Let's take a look at that. It's a device used to measure pressure, and it just works via the seesaw effect, or the balance effect. We have this liquid in here, you see, and if it were a true liquid, it would want to reach the same level. So this liquid level is higher, so what it wants to do is it wants to flow downhill. Liquids want to flow downhill, right? But what's preventing this liquid from flowing downhill is this gas that's trapped in here. And it's going to be the weight or the pressure of the gas. So if you see a seesaw, so somebody's sitting on this side of the mercury, and then somebody else is sitting. Who's sitting on this side of the mercury? Well, this is what we call open end. Do you know who's sitting on this side? The air. And so air sitting, how much does air weigh? 14.7, but it varies. It varies. It's not always 14.7, so that's why we have a barometer. Yesterday's pressure was a little less than 14.7. Yesterday's pressure was 750, I forgot, 758.4 or something like that. Something like that. So we measure, this is barometric pressure here. And this pressure is greater than barometric pressure. This one weighs a lot more, right? You see, because the seesaw is totally imbalanced. So what we do is we bring the seesaw into balance. So if we go horizontal like this, then this gas weighs just as much as the right side. So the left side weighs just as much as the right side. Well, how much does the right side weigh? The right side weighs the barometric pressure plus the weight of this mercury. So let's say barometric pressure were 760. Then I just measure how tall this is and then add it. So I'm going to have 760 millimeters worth of mercury plus this many millimeters worth of mercury. Does that make sense? How do you do minus? Like this? This would be, we don't do minus, we always do plus. This one is inverted the opposite way. So which one weighs more, the air or the gas? The air weighs more. So what we do is we bring it into balance like this. So now the right side weighs the same as the left side. And so the atmospheric pressure is equal to the gas pressure plus the pressure exerted by, or the weight of the mercury. Does that make sense? So all we do is we get a ruler and measure how many millimeters of mercury that is and stat it. And so here, we get two equations for this. So over here, the PG, pressure of the gas, is equal to the pressure of the atmosphere, PA, plus the pressure of the liquid mercury in millimeters of mercury, Hg liquid. Usually atmospheric pressure is represented in millimeters of mercury, so we end up with this equation here. I don't like this equation because I just like to add it here. So when I look at it, PA is equal to PG plus PHG, mercury. Okay, now I'm going to solve for PG. So PG is equal to PA minus PHG. And so that's where this equation comes from. So I always add it. The left side is equal to the right side. And we always add. And then to solve, we want to solve for PG. And that's what, so I don't bother memorizing two separate equations. I just know to add on both sides. Does that make sense? This is called an open-ended manometer. And so we can figure out the pressure of a gas. So here's some practice problems with pressure. If I have the pressure inside the steam boiler is 27 psi, express the pressure in atmospheres. So this is just a one-step conversion. 14.27 psi, and 14.7 psi, 14.70 psi per atmosphere. And so the psi cancels, that leaves us with atmosphere. So this is dimensional analysis. These unit conversions are most easily done with dimensional analysis. They ask you to check your answer here. We'll start doing that later. The pressure in an automobile tire is 29 psi on a day the weather report states that the barometric pressure is 30.09 inches of mercury. How would you report the absolute pressure in the tire to a colleague in kilopascals? Sometimes tires, like if you, I bought a bike tire, and the bike tire had kilopascals on the side. It was supposed to inflate it to like 150 kilopascals or something like that. So I had to do some unit conversion. Well, fortunately, they had PSI. But we have one more thing we need to talk about. If you bought a helium tank from somebody and you went home to fill a balloon with helium and then you opened the valve and no helium came out, would you be very happy? No, you'd probably return it and say, there's no helium in there. But then the person says, no, there is helium in there. Who's right? Is it possible that the person that sold it to you could be correct in stating that there is helium in there? Huh? Well, it doesn't matter how much, but there is helium inside the tank. So they sold you helium that was inside the tank. The only problem is, in order to get the helium out of the tank, you would have to suck it out. You would have to suck it out because, do you know why? Because if you say the tank is empty, what does that mean? If the tank is truly empty, what do you have inside the tank?
Nothing.
Nothing. If there's nothing inside the tank, what is the pressure of the tank?
14.7.
Zero. Zero means there's absolutely nothing in there. If there's absolutely nothing in there, remember, what was that submarine? The Ocean Gate. Remember the Ocean Gate? Wouldn't the tank crush from the weight of the atmosphere? It's possible. It's possible we could have an implosion. Because if it were truly empty, it would be a vacuum. And that would be what we call absolute pressure. What is the lowest absolute pressure that can be achieved?
Probably like 1.
The lowest absolute pressure that can be achieved is not 1, it's actually 0. If it's 0, there's nothing in there colliding. And so we call that zero pressure absolute. Zero pressure absolute is what we call PSIA. So if I have 0 PSIA, that means there's nothing in there. But the person that sold you the helium said there is something in there. You know how much helium is in there? They had 14.7 PSIA. But the problem is 14.7 PSIA. So if I had 14.7 PSIA of helium in here, out here I have how many PSI? The same. So if I have 14.7 versus 14.7, who wins? Nobody wins, and then no helium comes out. Helium might leak out, but whatever helium leaks out, air has to leak in. And so nothing comes out. And so you say the tank is empty, and they say, no, the tank is not empty. Because if the tank were truly empty, it would be a vacuum. And it could possibly implode, right? And so, then you bought helium, but it wasn't much. So the only way you can extract the helium is to suck it out of here. But that's not going to be very effective for filling balloons, is it? No. So we call this, a 14.7 is essentially empty because no helium is going to come out. And so we call that PSIG. So 14.7 PSIA is going to equal 0 PSIG. PSIG, G stands for gauge, A stands for absolute. And so we're talking absolute versus gauge pressure. So if I have 0 PSIA, what is the gauge pressure?
14.0.
Negative 14.70. Is there such a thing as a negative collision? We have a positive collision. Is there such thing as a negative collision? Let's say I had an automobile accident and I collided with somebody. Is there something called a negative collision? I can undo that? No, actually I did. I backed up into a wall. I'd like a negative collision so I could reverse the damage to the bumper, but unfortunately, just going to live with it. And so what negative 14.7 means is that there's no such thing as a negative. What happens is it just means it's lower than 0 psi-g. And so I'm 14.7 below 0 psi-g. Yeah, 0 psi-a. 0 psi-g, sorry. All right. I made a mistake with the colors. But this would be PSI-A should be black. 14.70 PSI-A. And then PSI-G I was doing in green. And so when I look at the dial of a gauge, the dial of the gauge would be something like this. I'd have two scales. One in PSI-A. So at 0 psi-A, then I'm at 14.7 negative psi-G. And then I am going to have 14.7 psi-A, which is going to be 0 psi-G. And so there are two scales. If you look at an automobile tire, and your automobile tire says PSI, 29 PSI, is that PSI-A or PSI-G? In other words, if your tire goes flat, your automobile tire goes flat, and you take the tire pressure gauge and you read it, and it's reading 0, is that PSI-A or PSI-G? In other words, when your tire goes flat, is there nothing in it, or is there still something in there? There's still something in there. If your tire goes flat, maybe it's crushed at the bottom where it hits the street. But did it lose its shape above? No. And so this might have gone flat. And so that means there's still something inside there. What is inside there? Air. The only way to get out that air is to put your mouth on the little thing and then suck out all the air. Then it's going to be truly flat. It's going to be really empty. But do you want to even do that? Yeah? All right. Yeah, actually, people like to fill their tires with nitrogen gas, not air. Helium, yeah, maybe helium would be good. Except the problem with helium is it leaks out so fast. It's like a balloon. Helium atoms are so tiny that if you have a plastic or rubber balloon, it doesn't last because the helium kind of worms its way out of the rubber. So I want to suck out all the air and then refill it with nitrogen, but it's not so easy to do. And so it's not really flat. And so do you know what this PSI, if it's reading 29 PSI, this is PSI-A or PSI-G? This is PSI-G. All right, we need to know that. On a day, the weather report states that the barometric pressure is 30.09 inches. This is absolute or gauge? This is absolute. Now, I have to be a little bit, the way gauges work is like this. The gauge is going to read 0 psi-G when the pressure of the gas is equal to the pressure of the atmosphere. And so if the atmospheric pressure changes, the zero changes with it. Because what we have is we have two opposing gases. You have the gas inside the tire and you have the gas outside the tire. And when they're equal, then there's no movement, right? But if there's an imbalance, then the gas inside might want to leak out or the gas outside might want to leak in. And so when the gauge just registers, it doesn't care what the outside is. The outside can change, and therefore the zero is always changing. It's not always 14.7. And so this is like if you bring a bag of chips, if you bring a bag of chips up to Big Bear, do you know, have you ever felt it? It starts to expand. Yeah, it gets bigger, and there's a lot of pressure in there when you open it, you know.
So if they're like shipping like chips up to Big Bear, is there any way of preventing that?
They just seal the bag tightly. Eventually it leaks out, you know, but immediately when you get up there, then it's going to be like this. And the opposite happens. If you have a dense bag of chips and you bring it down to sea level, it collapses in, you know. And so like a water bottle, I had a 1 gallon water bottle and driving down the mountain, get to the bottom of the mountain, you hear all this pop, you know. And then I look at my water bottle's crushed in. Have you seen that? Yeah. And so and so 0 psi down here at sea level versus 0 psi up there at Big Bear are different. So if you have a car tire, you inflated it to 32 psi G. Down here, you go up to the Big Bear, you measure the pressure, it's going to be higher. And so we do different things to figure. Okay, but this 30-point barometric is absolute because if we have 0 inches of barometric pressure, that's no pressure at all. How would you report the absolute pressure? So they're asking for the absolute pressure. So they give us 1 gauge pressure and 1 absolute. So how are we going to figure out what the absolute pressure in the tire in kilopascal? So first off, we want to figure out what is the absolute pressure on the gauge. So the gauge is reading 29 psi. So let's go ahead and figure this out here. Now, if the gauge were reading 0, is it really 0? No. So if we had 0 psi G, then we know that the absolute pressure is 30.09 inches of mercury absolute. Okay, so what we're going to do is I'm going to use some dimensional analysis. So we have 30.09. I want to figure out what that is in psi. So I'm going to go 30.09 inches, and then I'm going to convert from inches to what? Feet? Should I do inches to feet? No. Should I do inches to centimeters? We're not going to do square inches. We're going to just go inches to centimeters. So now I have centimeters of mercury, and then where do I want to go next? Millimeters. The reason I want to go to millimeters of mercury is because I know that there is exactly 760 millimeters of mercury per 1 ATM. Or there's exactly 760 millimeters of mercury in 1.01325 bar. But we're not going to go bar. Okay, and then 1 ATM is equivalent to how many psi? 14.70 psi. And so this is absolute. And so what is this going to give me in psi here? Yeah, I get 14.78. How many sig figs are we allowed? So how many sig figs in 30.09? 4 sig figs. How many sig figs in 2.54? 3 is incorrect. 4 is incorrect. How many sig figs in 1? Infinite. And how many sig figs in 2.54? Infinite. Why is it infinite? No, it's a definition. How many sig figs here? How many sig figs here? How many sig figs here? Well, the 1 is infinite. So in exactly 1 atmosphere, there are 14.70 psi to how many sig figs? 4. This is rounded. And so our final answer is allowed 4. So what we do here is I want to always show 1 extra digit. So it's 14.7829003. I'm going to just write 14.782 psi. And then I'm going to round this to 14.78 psi. Now, is this absolute or gauge? This is absolute. So I would write psi A. And so 0 psi G is equivalent to 14.78 psi A. Okay? And so that means we're offset. And so what I have to do is I have to take 29 psi G plus, what is the offset? 14.78 psi A. And so altogether I'm going to have 33.78 psi G. Or is no, this is not psi G, sorry, this is psi A. Let me erase that. So the scales are offset by this much. So 29 psi G is equivalent to 33.78 psi A. Because we're always off by 14.78. Now they want it in kilopascals, so we're going to have to figure that out. So I'm going to take my 33.78 psia, and then I'm going to convert that to atmospheres. Let's go with 14.70 psi per 1 atmosphere. Okay, then I'm going to convert this to pascals. No, I'm not going to convert. Actually, maybe I'll convert this to pascals or bar. Should I go bars or pascals? All right. If I go pascals, there's 101,325 pascals per atmosphere. And then I'm going to go to kilopascals. There's 1 kilopascal for every 1,000 pascals. And this is going to give me the absolute pressure in kilopascals. So it's going to be 33.78 divided by 14.7 times 101,325 divided by 1,000. And that gives me 232.84 kilopascals. I think my bike tire said 150 to 250 kilopascals. I don't remember. Because my bike pump doesn't read kilopascals. So I had to convert it. How many sig figs are we allowed? 4. So I'm going to write this as 232.8 kilopascals absolute.
That's okay.
I don't quite remember this. All right, with this. So gauge and absolute pressure are a headache. But the well, here it is. You can see. So this is their worked out solution here. I did it differently. You could do it different. Like this conversion factor, I don't have memorized. Here. I didn't bother with this conversion factor. I don't remember the inches either. I just remember the millimeters of mercury. I try to minimize the amount of memorization I could do. Could do that. So they got 300 kilopascals. Mine was quite a bit off. I got 232. I don't know. But what we want to do is we want to check. So I'd go back and double check my calculations because I could be off. So I'd go back and check my calculations. All right. We're going to take a look at the simple gas laws. The laws just come from empirical observations. So here's your observations. The observations is what are they doing here? Let's take a look at what they're doing. So they put a mercury plug here and trap some air. So we have some air trapped in here. And what they're going to do is they're going to change the temperature. So if you increase the temperature, what happens to the gas? It expands. Well, the mercury plug can move, and so the gas can expand. And if you cool it down, the gas can contract. So what they did was they just used the height of this mercury plug as an indication of the volume. And so the higher this mercury plug goes, the greater the volume. And so they got a height of 82 at 50 degrees C, and then they cooled it down and contracted. And it's hard. Do you see the pattern here? It's kind of hard to see the pattern here. So what we do is we'll just graph it and see if there's a pattern. Do you see the pattern here? Yeah. This is what we call a linear pattern. A linear pattern is defined by a straight line. And so if we write this in terms of math, then we can come up with the equation for this line, which would be the most concise definition for this. Y equals mx plus b. But instead of doing that, what we could do is something else. Y equals mx plus b. Well, let's try to figure it out here. Y is the height of the volume. And so I'm just going to call it the volume, not the height. The height, this is going to be proportional to the volume. M, then we have the slope here. Then X is the temperature in degrees C, and B is the intercept. So this intercept I don't see here, down here. Intercept. But this is what we could take a look at here. Do you have some of your data? It depends on if we do this. We can make our life a lot easier if we change something. If we use degrees C, this is not absolute temperature. However, if we use Kelvin, this would be absolute temperature. And so if I convert my degrees C into Kelvin, then the intercept is very easy. Because at 0 volume, we have 0 Kelvin. And so when I look at the intercept here, this is in degrees C. In degrees C, the law is more complex, more complicated. Because I got to figure out, it's still simple, but however, if I do this in Kelvin, then the volume is equal to mx plus b. The intercept here is 0 and 0. So at 0 Kelvin, I have 0 volume. So b is 0. So the volume is equal to mx. X is going to be the temperature in Kelvin. Here. M is a constant, which is the slope here. I'm not going to measure the slope. And so what we say is the volume is equal to a constant, which is the slope, times the temperature. In other words, this is what we call Charles' law. In Kelvin. Up here, this is Charles' law in Celsius. Which one's easier? Charles' law in Kelvin or Charles' law in Celsius? Yeah, in Kelvin, because we don't have to worry about this intercept term, which is for the offset here in the zeros. Here, the zeros are the same. And so we do this. This is one form of Charles' law. Another form of Charles' law is the volume over temperature ratio is always the same. So if I have a change in temperature, the ratio will stay the same. So if I change the temperature from T initial to T final, then this ratio's got to stay the same, and we can figure out what V final is. And so this is another form of Charles' law. Yeah. So these are the two forms of Charles' law that we use. Now, going back to our lab, this is what we want to do here in this particular calculation. In this calculation, it asks us to calculate the volume of air in the flask at T2 using Charles' law. And so let me do that here. So I want to use somebody's data. Insert slide here. Oh, you have data? Okay, go ahead and give me the data here. Let me do this. Let's just do trial 1. Temperature of boiling water. 105 is not precise enough. 105.0, was it right on the 5 line? Below or above? We have to measure the temperature to the nearest tenth of a degree C. The reason we have to measure it to the nearest tenth is it's easy to see 105 and 106 and 104. And so what we have to do is we have to read between the lines, or if it's right on the line, we call it 0. 105.6. When I see a 105.6 degrees C, I automatically think that this thermometer is miscalibrated. That's unusually high. And so this thermometer has poor calibration. But it's okay. You know why it's okay? it's okay because all we care about is a difference in temperatures. If you only care about a difference in temperatures, does it matter if it's miscalibrated? No, because that's what we call a systematic error. And so that means the high temperature and the low temperature are systematically off by the same amount. But the difference between the high temperature and the low temperature should be accurate. And so if it's always reading 5 degrees too high, then the low temperature is also reading 5 degrees too high, and those systematic errors cancel when we do the subtraction. Does that make sense? So it doesn't matter. If you want to measure the height of a mountain, you don't have to go to the center of the earth to measure the absolute altitude. You can do it from the base of the mountain to the top and then just subtract the two. You'll get the same answer as if you measured it from the center of the earth to the base and then the center of the earth to the top. It's a systematic error in terms of altitude above the center of the earth. So anyway, we do this. What was the temperature of the cold water? 27.7. So it looks like it's reading about 5 degrees too high, maybe. I don't know. What did other people get for the temperature of the cold water? All right, maybe a couple of degrees. Okay, what was the volume of water entering the flask? How many? 88 milliliters. Okay, that's okay. Here we can only be as precise to the nearest milliliter. Okay, what was the volume of the hot air? The volume of the hot air is equal to the total volume, which equals the flask plus the tube. Remember the tube? The glass tube? Yeah. We need the volume of that. And so what was this is the flask with the stopper. And what was that? Yeah. 476? Okay, so experimental volume of air in the flask at T2, V2. Okay, experimental volume of the flask. Okay, T2 is the cold. So this is the volume of cold air. The hot air filled the entire container, but the cold air didn't. And so this is equal to 476 minus 88 milliliters because 88 milliliters of water got sucked in. And so this gives us how many? $388 milliliters? Is that right?
Isn't it 398?
398? Yeah, 398. Report sheets can be done in pencil. I didn't talk about this that much. Report sheets can be done in pencil so you can erase things. However, your raw data needs to be in ink. It needs to be in ink because it's more permanent. So we have 398 milliliters. Do your calculation not on your report sheet, but in your notebook or on separate paper. You want to keep your notebook clean. I mean, not notebook. You can keep your notebook a mess. You want to keep your report sheets clean. Okay, now we're going to calculate the volume of air in the flask at T2 using Charles' law. So what we have here is V1 over T1 is equal to V2 over T2. So we're going to calculate V2. V2 is equal to T2 over T1 times V1. Now, are we using the Kelvin version of Charles' law or the Celsius version of Charles' law? We're using the, no, is this the Kelvin version or the Celsius version? This is the Kelvin version. So we have to convert our temperature to Kelvin. Yes. Or we use the Celsius version of Charles' law. You know what the Celsius version of Charles' law looks like? The Celsius, can you divide by 0 degrees Celsius? No. And so the Celsius version looks like this. It's V1 over T1 plus 273, which is equal to V2 over T2 plus 273. Which one looks easier algebraically? The Kelvin. So what we need to do is we need to convert our temperatures to Kelvin. To convert our temperatures to Kelvin, here, we'll do it down here. T2 is cold temperature. So this is going to be 27.7 plus 273. I'm going to be a little bit more precise here. It's 273.15. Okay, and then T1 is the hot temperature, 105.6, did you say? 105.6 plus 273.15 times V1. And so this is what temperature up here. We'll do 27.7 plus 273.15 divided by 105.6 plus 273.15. Let's convert into Kelvin. Times V1. V1 is the volume of hot air, 476. 378.09 milliliters. How many sig figs are we allowed? It looks like 3 sig figs. We're going to have enough decimal places here. So this comes out to 378 milliliters. Now the percent error, assuming the calculated volume is correct. So this is going to be our theoretical based on calculation. This is our experimental. And so the percent error is equal to the experimental minus the theoretical divided by the theoretical times 100%. So this is going to be experimental 398 minus theoretical 378 divided by the theoretical 378 times 100%. And so I'll take 398 minus 378, which gives us 20, divided by 378 times 100. And so we end up with 5.29%. And so this is 2 sig figs, so percent, which will round to 5.3%. Okay, with that? Now, 5.3%, is that bad?
Yes.
It's not bad, not terrible, because you think about the experiment, you know, there are lots of potential errors in this experiment, so this is not bad.
What's the percent error you would want us to do?
This is actually pretty good. I see people with 100, 200% error, then I start to worry,
I
yeah.
got a 149.
You got 149% error? That's kind of high. Yeah. Uh-huh. Part A, there's no part A in the data table. Okay. That's one part of this lab. The other part is we're going to make this. You know this plot here, this Charles' law plot? The Charles law plot says when the volume, what's the smallest volume you can have? Let's say you went to buy a balloon and they offered you a 0-liter balloon, but you say, I want something smaller than a 0-liter balloon. Can you buy something smaller than a 0-liter balloon? No. And so that's in theory, that's the smallest volume you can get. Like 0 liters of water. Can you have -1 liter of water? That's impossible for matter. And so this means that as far as Celsius temperature, we can't go below 0. And so do you know what the absolute coldest we can go in Celsius is? It's -273.15. And that's where this intersects. -300 is impossible. That doesn't exist because we can't go smaller. And so Charles' law tells us what absolute 0 is theoretically. It's going to be -273. Well, if that's the case, then Kelvin comes along and says, okay, if that's the coldest, we might as well just call that 0. Kelvin. And so Kelvin just said, okay, if that's the coldest, we'll call that 0, and then that's, in theory, the coldest temperature. If we did this in Fahrenheit, it'd be like -453 or something like that here, Fahrenheit. Okay, now what you're going to do is you're going to make a plot like this, and we're going to see where it intersects. It should intercept at -273 if we use Celsius, right? And so you have some graph paper here. Do you know what this is here? This is Charles' law in Celsius. And so this would be V1 over T1 plus X and V2 over T2 plus X. And so what we're going to do is we're going to use some algebra to calculate what X is. And hopefully it comes out 273.15, hopefully. But you know what I've seen? Not that. I mean, just crazy values of X. But hopefully trial 1, 273.15, and hopefully trial 2 comes out to 273.15. All right, so that's calculation A. The expected value for X is 273.15. Okay, the next thing we're going to do here is the graphical determination of absolute 0. So we want to see where the intercept is. The intercept should be at -273.15 degrees Celsius. And that's what's expected, but let's see what's observed. What's observed is you're going to make a plot here, and you're just going to graph it. So let me rotate this and then shrink it down. So you're going to plot your T2, which is about 100, and the volume, and your T1, which is about room temperature 25, and the volume. And you have 2 points here. From these 2 points, you're going to draw a straight line, hopefully intersecting at -273.15, which someone's going to call 0 Kelvin. And so hopefully it intersects there. But oftentimes what I see is people have to attach another page. And so they attach another page here, and then they hand draw blocks here, and they come out with an intercept of like -500, which is like way off, right? Way off because the percent error is so huge. And it's because the experiment didn't work so great. Maybe their finger wasn't there, or maybe they didn't seal it tight enough, or maybe they didn't allow it to equilibrate or suck in the water. Yeah. Anything close to -273 is great. Hopefully you don't have to add another sheet. Hopefully it doesn't go beyond -350. But these are impossible temperatures. You know, the temperature will just go here because the volume goes to 0. The smallest volume we can have is 0. Okay, with that. So that's Charles' law. Let me take a look. We have absolute 0, which is -273.15. Oh, sorry, -459.67 degrees Fahrenheit. molecular motion stop corresponds to zero gas volume. According to kinetic molecular theory, kinetic energy of the substance is zero at absolute zero. Here's a particulate view of Charles' law. And there's some more stuff. So I think what we'll do here is I'll probably stop here. And I'll give you the option here. You can work. What should we do? I know what I want to do. I'm going to stop here and we're going to look at the next quiz here. But the same kind of stuff applies. See if I still have it. Let's take a look at number 76 here. Fahrenheit and a Celsius thermometer are immersed in the same medium. So they're measuring the same thing. And so these are, at what Celsius temperature will the numerical reading on the Fahrenheit thermometer be? Let's try this one. B. Twice that on the Celsius thermometer. So what this means is this. If the Celsius were reading 100, then the Fahrenheit would be reading double that. And so if the Celsius were reading 100, the Fahrenheit would be reading 200. But that's false, because if the Celsius were reading 100, the Fahrenheit would actually be reading 212. But because they're offset and because the sizes are different, is it possible that there is a temperature in which the Fahrenheit is exactly double? How could we figure it out? We're going to use math. Because, and this is the third way of solving. So we have three major ways of solving problems. One, dimensional analysis. Two, an algebraic equation like the Fahrenheit equation or the Celsius equation. And three is what? Three is the system of equations. Two unknowns. If you have two unknowns, how many equations do you need? Two equations. And so let's take a look at this particular problem here. So I'm going to cut this out. And then we're going to try this. Well, I'll show you the first one, and then you could do the second one. One of these will be the quiz, and then we're going to do one more. I'm going to do B, and you do, which one do you want to do? B or A? Or I'll do A. Which one do you want me to do?
All four.
How about I'll do B? I don't know what the temperatures are. And so I need to know both, the temperature in degrees Fahrenheit and the temperature in degrees C. So we need two equations. Can you think of one equation? I can think of one equation. Degrees Fahrenheit is equal to 9/5 degrees C plus 32. That's one equation. Now I have to think of a second equation. Can you think of a second equation? What is it? All right, Jacob.
Degrees Celsius is equal to degrees Fahrenheit minus 32 divided by 1.8.
Yeah, we could do that. But that's not the equation I'm looking for because that's the same equation as this, just rearranged. I need something that's different than this equation. It's not rearranged. Okay,
You could say that Fahrenheit is equal to twice 2 degrees Celsius.
yes. The Fahrenheit thermometer will be twice the Celsius thermometer. So the degrees Fahrenheit is equal to 2 times the degrees Celsius. Okay, now we have two equations. What do? We substitute. And so I'm going to just go ahead and substitute. Degrees Fahrenheit is equal to 2 degrees Celsius, which is equal to 9/5 degrees Celsius plus 32. And then I'm going to solve for degrees Celsius. So 9/5 is 1.8. So 2 minus 1.8 gives me 0.2. Degrees Celsius is equal to 32 degrees. Degrees Celsius is equal to 32 degrees divided by 0.2 degrees, which is how many? So let's see. 32 divided by 0.2, 160. So the degrees Celsius is equal to 160 degrees C. And that means the degrees Fahrenheit must be double that. You see that? 160. Therefore, degrees Fahrenheit is equal to 2 times the degrees C,
Which is 320.
which is 320 degrees. So we can check this. Quick check. We'll calculate the degrees Fahrenheit. We're going to calculate the degrees Fahrenheit by plugging in 160 degrees for the Celsius plus 32. And so when we do this, I'm going to get 160 times 9 divided by 5 equals 288. So this comes out to 288 degrees plus 32 degrees. So plus 32 is 288 plus 32 comes out to 320, which is double the Celsius, right? And so it checks. You got it? All right, so which one do you want to do for your quiz? C? C or A? All right, whatever I want. All right, let's do A.
Whichever one, or we have to do A.
No, do A. Everybody do A. You can work together. Try to do A.